armed forces need to pack a punch on the battlefield. They bring out the big guns. Modern artillery is an age-old solution adapted to today's military objectives. And when 21st century armies unleash a barrage of artillery fire, there's plenty of high-tech weapons to choose from.
Long-range multi-barrel rocket launcher systems are very effective, and their importance cannot be underestimated in the conventional battlefield. MBRL systems are mobile launch vehicles carrying unguided rockets and provide the facility to unleash fire from anywhere, anytime. Long-range multi-barrel rocket launcher systems have many points in favor of their use. They can deliver fire from unsurveyed positions, lying off the launch tube cluster with the crew staying inside the cabin without using aiming points. Reduction of combat crew, increasing the survivability, and an effective and cheap way to disable enemy light armors and infantry within a specific area. Currently, Pakistan Army is using rockets having 20 km range to be used in MBRL systems, and it can deliver 20 kg package up to 20 kilometers. On the other hand, India is using rockets having 40 km range. Its caliber is 214 mm and it can carry up to 240 kg warhead to 40 km range. So it's far more effective than the Pakistani counterpart. So if Pinaka open up, the enemy in front of it may have to face serious consequences. The purpose to start this project is to defeat Pinaka or at least develop its rival MBRL system. Current caliber Pakistan Army is using is 122 mm. Our purpose is to develop a rocket of range 40 km which will be cost effective by staying within the confines of available caliber so that no other launch pads need to be designed. In short, a rocket is designed to be used in MBRL system. More specifically, an approach is established to design a rocket motor. In the present study, material has been selected for rocket motor case. The prime objective of this project is to design and develop such a rocket motor which could be capable of delivering 20 kg warhead and having range of 40 km to defend our lines from enemy Pinaka within being confined to available launch limits. Another objective is to select an economical material for rocket motor case which performs the required functions. An approach to establish rocket motor of any size has been discussed in the present study. Aluminium alloys are selected on the basis of their high strength to weight ratio, availability of raw materials and facilities available. From our knowledge of destruction mechanism of warheads and the battle history, we chose napalm. Napalm was first used by Arabs in the Third Crusade against Richard's army. It is then used in Second World War and in Vietnam War with the very successful effects. It is also used in 1967 Arab-Israel War when the Israel Air Force unleashed napalm against the Egyptian tank columns. Egyptian army is the eyewitness of devastating effects of napalm.
The napalm is a very cruel, very unpleasant kind of a bomb. We
saw like atom bomb. Suddenly, fire.
Essam Taraz was one of the Egyptian soldiers on the ground who witnessed the terrifying napalm attack.
All the sky was red color. Black and red, it is very difficult to explain.
Come on!
Guys, these are our two bombs and we are going to connect it with the wire.
Start हो गया?
So now we are going to blast. 1 minute. Raya? The destruction power of napalm can be seen with the neutralization of massive Egyptian tank brigades. A rocket has been designed keeping in mind the constraints of external envelope. The strategy we are following to design the rocket, more specifically the rocket motor, is shown in this figure. Starting from the mission requirements, we first evaluate the independent parameters, then the dependent parameters. After that we select the grain. After grain selection, there will be a stage to analyze the grain and check its dimensions. In the next step, we design the casing and choose its material, then final analysis and testing. The sequence mentioned here is not as simple as it looks like. It consists of long calculations, optimization and tedious iterations. Nearly at each step of rocket motor design sequence, iteration and optimization has to be performed. For demonstration purposes, we prepare a small size rocket, but due to lack of communication between fire controller and the photographer, we simply could not manage to capture the final launch movements. For material selection, this is the route we have followed. First we find out necessary performance indexes for the required properties. Then we scroll through the literature and find out 2 or 3 best performing materials for each performance index. After that we go for weighted average method and find out best performing material for the combination of properties. We select aluminium 202 for a while. Then we go for detailed analysis of material. We first find out the critical track length and calculate either it is within the range of NDT equipments to date. Then we find out either it is in plane strain mode or in plane stress mode. After that we go for UEL testing of material like tensile testing and fracture toughness testing. We perform tensile testing at 25 degrees C and the results are showing 5 plus minus standard deviation. Then we perform fracture toughness test. It is also showing 3.54 plus minus standard deviation. After the detailed analysis of material, we decided to go with aluminium 2024.